I'm happy to be here today to talk about Titan and the Dragonfly mission concept that we've been working on for the past few years. I've studied Titan for the better part of two decades at this point. I started studying Titan as part of the Cassini team, working with the Cassini cameras, the imaging science subsystem, and planning the observations of Titan with the cameras, and then also worked with the Cassini radar instrument as well. So it's been a real privilege to be able to explore this place that used to be such a mystery and has become so familiar to all of us through Cassini's exploration. And I am now the principal investigator of the Dragonfly mission concept. This is a mission that we've proposed to New Frontiers. That's the same program under which the Juno mission that's currently operating at Jupiter, the OSIRIS-REx mission that just got to the asteroid Bennu, and the New Horizons mission that just flew by MU-69 in the distant reaches of the outer solar system. This is the same program that those missions have flown under. At this point, we are in the last part of the competition. 2 missions were down-selected from the first group that were proposed, and those 2 missions have had another year of study, and we're coming up on our site visits, which is the last part of the last step in the competitive process, and NASA will be making a decision on what mission to fly sometime this summer. So hopefully we'll be able to fly. So Titan is one of the moons of the planet Saturn. You can see, this is a natural light. This is what Titan would look like to our eyes. There is. Thank you. Thank you. I also can use this one, if I get it right. There we go. Yes. So there's Titan has an atmosphere. I'll talk about that a little more. And at visible wavelengths, the haze in the atmosphere obscures the surface. So Titan has been quite a mystery up until recent times. So why do we want to go to Titan? We don't know how life came to form on Earth. And we can't study the prebiotic chemistry on Earth because it's all overprinted with all of our biology. So we look to other places in the solar system that provide pieces to the puzzle of how of the chemical processes that led to the development of life. And Titan, chemically, is the most like the early Earth. It's the place in the solar system that offers us the same chemical building blocks that were available on the early Earth. So it holds keys to understanding our chemical origins. So here's Titan again. It's the largest of Saturn's 62 moons, and not only does it stand out, of course, because of its size, it stands out because it has this atmosphere. So Titan is unique in the Saturnian system. The atmosphere was first discovered early in the 20th century. Hints in observations suggested just after the turn of the century, that there might actually be an atmosphere at Titan, and that was confirmed by detecting methane in the spectrum of Titan in the 40s. So it is not only unique within, as I said, the Saturnian system, but it's unique within the, if I can find the pointer, there we go. There we go. It's unique within the other satellites in the solar system. So these are its cousins, the Jovian satellites up here, the Galilean satellites at Jupiter, and of course our moon, and Neptune's moon Triton. These are all to scale. Again, there's a lot of variety in the outer solar system, or in the solar system in general. It's a fascinating place, but again, Titan stands out because it has this atmosphere. But this doesn't just make it unique among all the satellites, it makes it unique among planets as well, among the worlds in our solar system. Again, these are all shown to scale. Titan's atmosphere is actually the second densest in our solar system after Venus. It's denser than our atmosphere here on Earth. And the surface pressure on Titan is actually 1.5 times the surface pressure here on Earth. So it actually has, it's a world unto itself in this sense. And you can see here, it's actually just between Mars and Mercury in size. Another thing that's large about Titan is its year. Saturn's orbit around the sun takes 29.5 Earth years. And in that time, the Saturnian system is tilted. It's actually tilted a little more than the Earth is. And so in that time, you can see at the top here, the way the rings, this is what Saturn would look like from Earth, over its year. So the rings open and close, and with it, the entire satellite system go through the same kind of pattern, the same seasons that we have here on Earth, except you can see that the seasons on Titan are much longer. So the northern winter solstice was in October of 2002, the equinox in 2009, and we just passed the northern summer solstice in 2017. So it's a very extended season, but nonetheless, a fascinating process that gives it another aspect of Titan that's very Earth-like. Titan's day is actually 16 days long. It's tidally locked to Saturn, so the same face of Titan always faces Saturn, and it takes 16 days to orbit Saturn. So the same side of Titan always faces Saturn, like our moon. There is a small tide on Saturn, but Titan is much smaller than Saturn. But like our moon, so Titan and Saturn, it's the same, similar to the tides on Earth. There is not, but the atmosphere will move the same way that our atmosphere moves. The chemical composition of Saturn is gaseous. It's gaseous in the atmosphere. So there. Yeah.
Why don't we wait to the end for that?
That's okay. So I wanted to put the exploration of Saturn and Titan in the context of the year, of Saturn and Titan's year. So this again just shows the year starting from we'll start from the winter solstice, running through the northern vernal equinox, the summer solstice. The exploration of the Saturn system by Pioneer and the two Voyagers was around the northern vernal equinox in Titan's year. And the Cassini spacecraft got there arrived at Saturn in the summer of 2004, and the Huygens probe explored Titan in the early part of 2005. So this was actually just after the winter solstice. Cassini, the spacecraft, was operating well, and so the mission was extended through the equinox. So we called that the Cassini equinox mission, extended through the northern vernal equinox. And the spacecraft was still healthy, still functioning well. So there was another mission extension. So Cassini, all told, spent 13 years in the Saturnian system, which is a good portion of a Titan and Saturnian year. So that was really valuable in order to understand Titan as a system. And so the solstice mission took Cassini all the way through the summer solstice in May 2017, a few months later, before the end of the mission. So this is our view of Titan as of the Voyager 2 observations. It wasn't until the 90s that we finally got a glimpse of what was underneath the haze. I will actually take that back. It turns out Voyager did detect the surface, but you had to know what the surface looked like to prove that it saw the surface. So we technically did see the surface with Voyager, but we didn't know it until we saw the surface with other detectors. So the Hubble Space Telescope, looking at Titan out in the infrared, made the first map of brightness on the surface of Titan. And later on, as adaptive optics improved, we got other images of the surface, maps building up of the surface. So we saw finally that there were bright areas and dark areas on the surface of Titan. So this was important because it wasn't known at the time whether the surface might be covered with a liquid methane ocean, whether it might actually not have land features at all. So the fact that we saw the same features, that they were stable from time to time, suggested that there were indeed land features on the surface of Titan. So the Cassini spacecraft and the Huygens probe were both designed to explore Titan. Cassini, of course, was designed to explore the entire Saturnian system, not just Titan, but there were a dozen instruments on Cassini, a dozen remote sensing and in situ instruments on Cassini, and another half dozen on the Huygens probe shown here. Cassini, for scale, you can see, oops, where's the pointer? There's a desk here. So Cassini was a good-sized spacecraft. And as I said, it spent a long time in the Saturnian system. And this plot over here, that's very busy, shows all of the orbits that Cassini did at Saturn. So you can see it changed inclination to be able to look down on the poles, to be able to look at things within the ring plane. And you can see just how much time and how much exploration it did in the system. During this time, there were actually 126 close Titan flybys, which sounds like a lot, and it was a lot. It was a lot to plan. But Titan is a really complex system, and the number of questions we still have about Titan after 126 flybys is daunting. So Cassini had a number of instruments that were designed specifically to be able to explore Titan as a system, to understand its surface, to see what's beneath the haze in the Titan atmosphere. The cameras, the imaging science subsystem here, were designed with a filter, a specific narrow band filter out here at 938 nanometers in one of the gaps, one of the windows in the methane absorption spectrum. And this allowed us to see the surface. So this is what Titan looks like in kind of real color, what our eyes would see. And this is what you can see if you actually start looking out into the infrared. Not only did Cassini have infrared filters on the camera system, which revealed the surface in all its glory, there was a visual and infrared mapping spectrometer that actually was sensitive out to 5 microns, so much longer than the wavelengths our eyes can detect. So Titan is limited. You can't get a full spectrum from orbit because you have you have to see the surface in windows in the methane, and so that's what these gray bars are. So there were several windows down to the surface spectrally. And using those, the VIMS instrument was able to build up a map of the surface as well. So this shows us the variability of materials on the surface. And this is designed, this is an enhanced color view designed to bring out these differences. What we don't know is the detailed composition of these different materials. We know there's a lot of organic material on the surface. We know there's organic material mixed with water ice, but we don't know the detailed compositions and the distributions. Well, we know the distributions, we just don't know what they are. Cassini also had a synthetic aperture radar, had a radar instrument, had multiple modes, including altimetry, as well as synthetic aperture radar. And so what you see here in these noodles, these strips, are ground tracks built up by SAR imaging during any given flyby. So we've Cassini imaged several tens of % of the surface with the radar, as well as the global imaging in the near infrared. So a few other facts about Titan. I showed you the size of Titan compared to the other satellites in the solar system, compared to our moon and planets. The surface gravity on Titan is about 1/7 that of the gravity here on Earth, because it's a smaller moon. And as I said, the atmospheric pressure is about 1.5 times the pressure here. The surface temperature out in the outer solar system is not high. The surface temperature on Titan is 94 Kelvin, or minus 290 Fahrenheit. And at these temperatures, the bedrock composition is water ice. So Titan, the system on Titan is composed of very different materials than we're used to here on Earth. We're used to water ice. But the interplay of these materials, the water ice here isn't rock. The liquid water here on Earth isn't lava. And so it's a very different set of materials acting on Titan. Beneath the surface, there's also a liquid water ocean. There's a deep liquid water ocean in the well beneath the surface. So it is among the ocean worlds in the outer solar system. As we've learned over the last few decades, many of the satellites, many of the icy satellites in the solar system have oceans in their interiors, and that's another reason that they're particularly interesting targets. So this is what Titan looks like in the near infrared. Or if you're down beneath a haze, you'd also be able to see this. So you can see there are a lot of dark regions at about the equator, and then there are dark regions at the poles, more at the North Pole than at the South Pole, which is particularly interesting. There's a little one here. Not terribly little, actually. It's about 200 kilometers across. So we'd been seeing these features on Titan for, since the 90s. We've been observing them, but we didn't know what they were. We didn't know what landforms there were making up these features. You can see a few that are familiar, right? There's an impact crater here. There's an impact crater here. There's one there. But like Earth, there are not a lot of impact craters, which is intriguing, because the reason there aren't a lot of impact craters on the surface of Earth compared to the Moon or other bodies in the solar system is because there's active geology that erases them. So on Titan, that suggests that there's a fairly young crater retention age and that there's active geology, active geologic processes erasing the craters. But if you look at this, like many bodies in the outer solar system, nothing jumps out as an obvious pattern in terms of the geology. So the vast equatorial region, those dark regions around the equator of Titan, turn out to be the biggest Zen gardens in the solar system. They're giant seas of longitudinal dunes that wrap all the way around, almost all the way around Titan's equator, except for this bright feature, which is that same bright feature we saw in the early imaging from HST and Keck, it's called Xanadu, and it's a very different geologic feature. But all of these dark areas around the equator are these seas of sand dunes. And what's fascinating is that these sand dunes, the sand on Titan, which is about the same size as sand on Earth, the sand on Titan is organic. We don't know how the sand particles form. We don't know if it's aggregated aerosols from the atmosphere that somehow grow, that there's some process that lets them grow to be large enough to be sand-sized particles that can saltate on the surface of Titan. It's not, it's organic. It's organic material. It may be organic material mixed with water ice. On sand, on Earth, sand is broken down. It's eroded from the bedrock, the silicate bedrock. On Titan, perhaps the sand is eroded from the water ice bedrock, but somehow those sand grains have to get covered in organic material because they're not water ice. So this is one of the mysteries we still have about Titan, is how you form the sand on Titan. Nonetheless, there are these spectacular fields of longitudinal dunes on the surface, and this type of dune is one that is less familiar perhaps to us. It forms in a regime where you have the wind coming from one direction primarily and another direction, and so the sand is actually migrating longitudinally along the dune. There are a few places on Earth where we have analogs. Namibia, there's some excellent analogs for longitudinal dunes, and there are some in the desert Southwest as well. But it's a fascinating process and something that is so familiar and yet composed of completely alien materials to us. So I mentioned there are a few impact craters. So you can see some of them here. This one is about 80 kilometers across. This one's a little larger. The impact craters have a similar progression to what we would expect. This is the largest one, which is about 400 kilometers across. They have a similar progression to what we expect in terms of the morphology, the shape of the impact craters that we see with this progression you see with size on other bodies. But you can see, especially in this case, how degraded, there's sand dunes forming here near the ring here, and you can see that the rim is cut in places. It's very similar to the types of degradation we have here on Earth. There are also some mountainous areas. This is the Mithra Montes, which is about 11,000 feet high in one of the maximum height in this area is that. You can see there are three ranges here that parallel each other. The tectonics of Titan are not well understood. And this is another area where there are tectonic features, or what we, presumably tectonically uplifted mountains. Again, you can see the complex interplay of the geology. This is very like Earth, where you have all of these different geologic processes overprinting each other, which is fascinating, but makes it much harder to understand the geology. And of course, here on Earth, we can go out into the field and we can do subsurface sounding and we can get information to put together that puzzle. But on Titan, we're right now just looking down at the surface. And so teasing out all these relationships is fascinating. There are hints of cryovolcanism. Cryovolcanism is cold volcanism, volcanism wherein the lava, in the case of Titan, would be water ice, not water ice, water, or perhaps a water-ammonia mixture. And this data here, this is a combination of the radar data. So you see the dunes here in the radar data, and these three stripes along here are just seams in the radar data. But this has been combined with the VIMS spectral information. And so you can see that there's a feature here and a potentially flow-like feature here. This looks very similar to the morphology of volcanic features on Earth. And this is a three-dimensional view of the same area. So this is Sotra and Doom Mons. So you can see there's a quite large pit here at Sotra, over 1.5 kilometers deep, right next to a mountain that is almost 1.5 kilometers high. So it's possible that you have an impact crater that just happened to hit, and form right near a mountain. It is perhaps more likely that these are related, and this is actually a cryovolcanic feature. But we don't have conclusive evidence. It's one of the mysteries that remains after Cassini. We also see all over the surface channels. This is a radar image that shows, in this case, that the channel floors are bright. That's in the radar at 2.2 centimeters on Cassini. Bright means rough. So, and means rough at about 2.2 centimeters. So this is kind of a gravelly or cobbled surface at the bottom of these channels. You see up here, the channels are dark. They flow into large dark features. The North Pole has seas of liquid methane. And the reason that these channels are dark is because in cases they're flooded with liquid methane flowing into the seas. And then this image is actually a near-infrared image. Oops, I lost the pointer. This is a near-infrared image. This was taken by the Huygens probe during its descent through the atmosphere. It was designed to study the atmosphere of Titan, to do imaging on the way down to the surface. And as it descended, it took these pictures where you can see channels on the surface. These dark channels are probably not flooded. These are dark channels because the floor was actually dark in the near-infrared. This is a couple of different maps. This is the radar map. Again, so you see these swaths from the radar observations. And then this is a near-infrared map taken by the ISS, the Cassini camera. And so you can see you see a lot of the same features, which is intriguing. That tells us something about the nature of the material, the fact that it's dark, things that are dark or bright to both wavelengths, or things that are different at both wavelengths as well. So there's a lot we're still trying to understand about Titan. But what you're seeing here at the North Pole are these three seas: Punga Mare, Ligeia Mare, and Kraken Mare. Kraken Mare is about 1,100 kilometers long. And then on the other side, there are these all these little lakes. It's a lake district on Titan. Why some parts of the pole have these giant seas and other parts have lakes is another mystery. And whether the connections, or there may be hydrologic connections between the different basins that we see, between different sets of lakes on Titan. Again, very similar to the geology on Earth, where you have hydrology as well. And there's a methane cycle. So not only might there be methane hydrology connected beneath the surface, methanifers or methane aquifers, there are also methane clouds. You can see this is actually a movie over here showing the clouds here. It's kind of evolving over a several-hour period. And this is another more dramatic observation of clouds. One of the mysteries that remain is why, at this time of Titan's year, which was northern summer, we didn't have clouds forming and raining at the North Pole, because that's what we would have expected, and it's what we saw at the South Pole in Titan's southern summer. So another outstanding mystery is the nature of Titan's atmospheric circulation. And these clouds, twice during the Cassini mission, we actually saw evidence of rain on the surface of Titan. There were twice we saw, once right during southern summer, we saw rain at the South Pole. We saw a dark area at the South Pole that came and went right after a large cloud outburst. And similarly, we saw something at lower latitudes around the equinox. So we know that the weather patterns change over time. The outstanding mystery, or among the outstanding mysteries, is why at this point we didn't see more weather at the North Pole. Titan's atmosphere, I mentioned, it's denser than Earth's. Because the gravity is lower, it's much more extended than Earth's atmosphere as well. So these are Earth and Titan compared side by side. You can see Earth's mountains are much higher, nice tall silicate mountains as opposed to nice short icy mountains. But the atmosphere extends much higher. And in this case, we're just showing the troposphere. Titan's atmosphere is extended enough that the lowest Cassini got was about 900 kilometers altitude. And it took a year of planning to figure out the best way, how low we could go and how we had to orient the spacecraft to keep it safe, because there would be so much drag at that altitude. So it's a very different atmosphere than what we're used to in that sense. This is an artist's rendition, obviously, of the Huygens probe. The Huygens probe, as I said, was designed to study the atmosphere of Titan, to descend down through the atmosphere, and to also take images of the surface and potentially make measurements of the surface if it survived. At the time the Huygens probe was designed, we didn't know if it was likely to land in liquid or on a solid surface. So the surface science package on the Huygens probe was actually designed to be able to make measurements of a liquid and to float in a liquid that we might predict to be on Titan, liquid methane, or to land on and make measurements of a solid surface. In the end, the surface where Huygens landed turned out to be solid. This is the image that was the area of the surface that was imaged by Huygens with a similar image of the moon to scale, just so you can get a sense of where, of what the scale is here of these features, these cobbles, which are probably water ice cobbles, and gravels here, and then extending out. Looks very much like a floodplain here on Earth, or perhaps a floodplain on Mars. It's a very similar, a very familiar view. And these cobbles are rounded the same way we have rounded cobbles here on Earth, which suggests erosion by through a fluvial process. So over the years of exploration with Cassini, Titan went from being this mysterious haze-shrouded world to being a very familiar world, a world with all of these different types of geologic features that are very much like the geologic features we're used to on Earth. Very similar processes occurring despite the fact that the materials are fundamentally different. And part of the reason for the difference in these materials is Titan's atmosphere. And this is this gets back to why we want to go back with the Dragonfly mission that we've proposed. The methane in Titan's atmosphere breaks down at the top of the atmosphere and recombines to form incredibly complex molecules. And these molecules were sensed by Cassini even at 900,000 kilometers altitude. It's very complex chemistry in the upper atmosphere of Titan. And these aerosols fall out onto the surface of Titan. So the complexity of Titan's chemistry is really second only to Earth. So these dials here show on the left abundance. This is the abundance of carbon at any given system. So Saturn wins because Saturn's a lot bigger than all of the others in this compilation. But the left-hand side of the dial here shows the complexity of the carbon molecules. And you can see from measurements that were made on Titan by Huygens and INMS, the degree of complexity up here, the level of proteins, is just outstanding if you want to be able to study the chemistry, the prebiotic chemistry. Yeah?
What is AMU?
Atomic mass units. It's the size of the molecule. They're very similar chemically, absolutely. Yep. So that's why Titan provides a destination where we can take the next step in answering fundamental questions like what makes a planet, or a moon in this case, habitable, and what chemical processes led to the development of life. Because we know that Titan has all the ingredients necessary for life as we know it. It has energy in the form of sunlight that drives this complex photochemistry in the upper atmosphere. And that generates this abundant and very complex organic material in the atmosphere that then falls out onto the surface, where it has the opportunity to mix with liquids, with solvents, which is what you need for life. And one of those solvents is liquid water. We know there's liquid water in the ocean, deep in Titan's interior. But there's also the potential for liquid water to have been on the surface, mixing with organic materials in Titan's past. There are potential cryovolcanic systems where you get eruptions of liquid from the interior onto the surface. And of course, there are also impact craters. And impact craters melt the target rock, and the target rock on Titan is ice. And so you get large pools for extended periods of time of warm water that can mix with this rich organic material. There's also another solvent in the form of the liquid methane on Titan, in Titan's atmosphere, on its surface. And methane, too, could support the development of a biological system, not life as we know it, but exotic life. So there's actually the potential for two different types of prebiotic chemical systems on Titan. So Titan has been doing chemistry experiments for hundreds of millions of years. And what we want to do is go pick up the results. And Cassini has showed us where to look. We know there's an Earth-like variety of geologic processes that leads to diverse surface materials, diverse surface environments. And what we want to be able to do is take a capable instrument suite from site to site to be able to make measurements of the chemistry on the surface of Titan, like one does on Mars with the Mars rovers. Mobility is key to being able to make these measurements on Titan. So that's why we've proposed Dragonfly. Dragonfly is a rotorcraft. It's technically an octocopter. It's got 4 pairs of rotors. And this allows us to fly from place to place, to take advantage of Titan's atmosphere, not only for the scientific richness that we get on the surface of Titan, but also for the means to be mobile, to get from place to place. We'd bring everything with us. You see there the high-gain antenna being deployed and then being stowed for flight, because Unlike most spacecraft, this spacecraft actually has to have some amount of aerodynamic design. And the reason we can do that is that it's easier to fly on Titan than it is on Earth. On Titan, you could put on a pair of wings and you'd want a sweater and you'd want some oxygen, but you'd be able to fly. It's the easiest place in the solar system to fly. Heavier than air mobility is highly efficient, and this is because of two factors. One being that the atmosphere is denser, and so that reduces the wing area you need to be able to fly. And the other is that the gravity is lower, so you don't need as much power to fly. So that's why we designed this mission concept as a lander with aerial mobility to be able to do wide-ranging exploration across the surface of Titan. The flight regime on Titan is actually very familiar. So you can see here, in terms of the Reynolds number and the airfoil speed, here's where Dragonfly would be between birds and ultralight aircraft and human-powered aircraft and wind turbines. It's a very well understood flight regime. And the control electronics we have, the drone revolution that allows any of us to get a drone and play around with it, that means that the technology already exists. This looks like a new concept, but what's new about Dragonfly is the application of existing technology to a new environment. And we have the ability to actually test as you fly, literally, by flying under terrestrial, on the Earth, but in facilities that can mimic the Titan environment. So we can test different aspects of the system directly in Titan-like conditions. This mission concept combines previous exploration strategies. It has been 2 decades that people have thought about flying on Titan, and in fact, one of the first ideas that came up was a helicopter. But there have been all sorts of studies of airships and hot air balloons and even an airplane. And most of the flagship mission studies that have been done incorporated different combinations of these exploration strategies. But with Dragonfly, we get the best of both worlds because we have the mobility, the ability to fly through the atmosphere to make measurements of the atmosphere. And we have a lander that can make the measurements on the ground. So the science that we would do on the surface of Titan, the focus of this mission is the prebiotic chemistry and the habitability of a world in the outer solar system. We want to be able to measure the chemical components and processes at work that produce biologically relevant compounds. To understand the chemistry of Titan, we also need the context of the environment that we're in. So we want to be able to measure atmospheric conditions, to identify methane reservoirs, to determine transport rates across the surface of Titan. We want to understand the processes that mix organics with past surface liquid water reservoirs, or even the subsurface ocean. And if chemistry actually did take the step from chemistry to biology, we'd like to be able to identify the chemical biosignatures of that biology. So to do this, we have a suite of 4 instruments. We bring with us a mass spectrometer. This is a mass spectrometer built by the Goddard Space Flight System, the same team that built the SAM mass spectrometer that is on the surface of Mars currently, active with the MSL mission, Mars Science Laboratory, or Curiosity. And with this system, we are able to sample the surface material to perform a detailed chemical inventory of what we have on the surface of Titan. Because Titan has an atmosphere, we can use pneumatic transfer. So we'd have drills on each skid, and those drills can be used to dig into the surface, and then we can just, like a vacuum cleaner, pull the sample right into the mass spectrometer. We also have a great cold sink. The surface of Titan is very cold, and so we can use that to make sure we keep the samples cold until they're in the mass spectrometer. Another thing we do is take a gamma ray and neutron spectrometer. These are usually flown on orbital spacecraft, like the Messenger mission that studied Mercury. But we can use this on the surface of Titan to measure the bulk elemental surface composition under the lander at any given landing site. And that gives us a much quicker analysis of classification of the surface material that we're landed on. One difference for this application is that we need to bring a neutron generator with us because Titan's atmosphere shields the cosmic rays out. So we have to bring our own neutrons with us. But other than that, this application allows us to do a classification of the surface before we do the sampling to do the detailed chemical measurements. We'd also have a suite of meteorology, geophysical, and seismic sensors. Meteorology, because we want to understand the nature of the atmosphere. We want to understand the atmospheric context for the system, the chemical system that we're measuring. We can also measure surface thermal properties, dielectric constant, to understand the nature of the surface material. And we'd bring a seismometer as well, so that we can actually sense Titan quakes, if there are any. There's actually been a lot of work done recently, both for the InSight lander that just arrived at Mars last fall, also for the potential Europa lander that has been under study, because one of the things they would like to do with that mission is measure Europa's seismic activity. And so there's been a lot of work done to understand how seismic waves would propagate in an ice shell, which is fascinating in its own right. And for this reason, we'd want to be able to sense if there are Titan quakes to understand the interior. And of course, because we can fly, we have the ability to do atmospheric profiles as well. So we can monitor the atmospheric conditions at our landing site. We can look for diurnal and spatial variations and also vertical variations. And then, of course, we'd have a suite of cameras. The camera suite be developed by Malin Space Science System based on a lot of the cameras that are already on the surface of Mars. We'd have a suite ranging from a microscopic imager that would allow us to image at very high resolution the area where we're sampling the surface material, and then a range of cameras around looking forward, looking downward. We'd also have 2 panorama cameras on the high gain antenna you see deployed here. The high gain antenna, because we're doing direct to Earth communication from the surface of Titan, the high gain antenna has to be articulated to be able to point to Earth in the sky. And that means we can leverage that articulation system to point the cameras around and build up a panorama of each landing site. We also have, because we have the forward and downward cameras, these are designed to do imaging on the surface, but also to do imaging in flight. So you can see the holes here, the windows into the interior of the lander where the cameras are looking down and out. So we'd be able to do aerial imaging as well. The mission in the New Frontiers program, the launch date would be 2025, with a Titan arrival in 2034. It's a long-term mission. It's a long way to the outer solar system, especially when Jupiter's not in the right part of the solar system to do a flyby. On the other hand, this arrival date is a Titan year after the Huygens descent. So we have atmospheric ground truth, if you will. We know what the atmosphere was like at this time of Titan's year and what the atmosphere was like at roughly this latitude on Titan. So we can use that in the designing our system. Yeah? Slime that is dry enough to be able to saltate to form dunes.
Well, the question might obscure your chemicals.
So at these temperatures, it would be dust. And yes, we absolutely have mitigation strategies. It's like sand.
You have a sandblast problem.
We have sand. It will not be sand blasting because the atmosphere is dense enough that this is actually.
Isn't the problem?
Yeah, it's not like landing, it's not like landing on Mars where you've got retro rockets, right? It's not that kind of velocity. It's a much gentler. So we do have to worry about dust, and we have mitigation strategies to make sure that we don't get dust, but we wouldn't have that kind of erosion. And also the materials that are being, that would come up from the surface are organic, so they're not as hard as sands, as silicate sands. So we can do experiments. There's a lot of experimental work that we can actually do to understand the nature of the particles. And we do that especially for the sampling system.
How's one of the winds?
The winds on Titan are, comparatively to Earth, very gentle. The atmosphere is very sluggish because it's dense and because Titan's rotation rate is so slow. So the diurnal variation, the day-to-day temperature, the day-to-night temperature variation is less than a Kelvin. And the seasonal variation in temperature is also on the order of a Kelvin. So we don't see these, we're used to a very dynamic atmosphere here on Earth with high winds and storm systems, and we don't have that level of activity on Titan. We also know, because of the Cassini observations and now Earth-based observations, what the seasonal pattern in weather is like and where you would most expect to see clouds and rain at any given time of year.
How long did it take to form those?
The dunes, longitudinal dunes, are a very long-term landform. So this is a landform that requires arid conditions primarily over millions of years.
What is the temperature variability across different spaces in Titan? Is that also on the order?
It's on the order of a Kelvin. It's kind of boring, really, in terms of just the variation. We're used to variation with altitude. There's a little bit of variation with altitude. There's a little bit of variation with latitude and time of year, but it's we would barely notice it. I will, yes. Yes, so the scale of the lander was one of the questions. The lander is rover-sized. It's Mars rover-sized. It's easy to fly on Titan. This is not the same kind of drone that we're used to playing with. This is a good-sized rover, except that we fly. The range depends on a lot of different factors, that we would balance in our exploration, because one of the things that we can do with this system is scout ahead. And so, in fact, I'll go ahead to another slide. This shows our operation strategy, where from any given landing site, going to another previously scouted landing site, we would actually go further and scout a new landing site, because we have the ability to look ahead and see where we're going to make scientific decisions, as well, decisions about the scientific value of the landing site, as well as landing site safety. So there are a lot of factors that go into how far we would travel at any given time. But in general, we would be able to, over the lifetime of the mission, we'd be able to travel tens to hundreds of kilometers. And there was another question about the how we stay warm. So yes, so Titan is cold. The power source that we would use is an MMRTG, a multi-mission radioisotope thermal electric generator, the same system that we're using on Mars in the MSL Curiosity rover. And that puts out a lot of waste heat. So I'll go back. So the lander is well insulated so that we can keep the instruments inside at a comfortable temperature. And so we actually can leverage the temperature on Titan to keep the things that we want to have cold, because we have an abundant cold sink all around us, and the things we want to keep warm, because we can use the waste heat of the MMRTG. Yes, so as to the extent possible, things will be encapsulated. And then, of course, we pay attention to the way the materials behave at temperature, or we heat the system.
Are you saying that there's a pretty good bet that there's microbial life on Titan?
No, I'm not saying that. I'm saying there's a really good bet that there is prebiotic chemistry, like the chemistry that occurred on Earth, that led to the development of life. And that's what we want to study. We have, with the mass spectrometer, with our instrument suite, we would have the ability to detect multiple chemical biosignatures were there actually to be, or have been, some sort of life on Titan. But we do not say, we do not predict that. That is, well, I don't know how one would necessarily predict such a thing. It's the prebiotic chemistry that is the focus of this mission, and we know for sure that that's already there on the surface waiting for us. We don't generate enough heat to change to, yes, it's a simple thermal problem to assess how much heat we put into the Titan environment. We do bring heat with us. We do heat the lander. This is a very small system compared to the scale of Titan. We are not concerned about affecting the climate on Titan, no. Correct.
Just curious, was there any thought putting a magnetometer because that would help the detector?
Yeah, it's there's so many things we would like to be able to put on the lander, but we have tried to keep focused because this is a focused mission in a focused mission program, and so the focus is on the prebiotic chemistry with the measurements of the with additional measurements to give us that context. But unfortunately, although there are a lot of other things we can think about that are small and lightweight and don't take a lot of power, we are mass constrained and power constrained and cost constrained, and so not everything is on the lander. So we are still in a competitive process. So we are not discussing all of the specific details of the mission in openly yet, simply because we're still in a competitive process.
So great job. I'm rooting for you guys. So 2 questions: are you going to risk taking it over a liquid body? And secondly, what does a methane lake even look like? Is it blue? Is it brown? Like, what do you think?
So the surface of Titan looks, I'll answer the first question first, the second question first, which is that the surface of Titan, to our eyes, would look kind of brownish, right? Like the image I showed you of the surface from the Huygens probe, that was actually processed to look similar to what we'd see. And the methane, if there wasn't much methane, you'd be able to see through it. Otherwise, it would look dark if there's a lot of methane. So I'll talk about the time scale, and that will get to your question about whether we go to a liquid body. So, like I said, we would get there in 2034. Because we have an MMRTG, which is a long-lived power source, we would plan for over 2 years of exploration. But we're landing in the equatorial dunes. We do that for a number of reasons. Chief among them being that we know that we have 2 kinds of material of very close proximity, because the dunes themselves are organic and the interdunes have a water ice component. So this is the Namib Desert. These are both images. This is not Titan. This is the Namib. And you can see how these longitudinal dunes, how much space there is, right? This big flat area, which is a different composition than the dunes themselves. And so we have the same thing on Titan, where the interdune materials have a water ice component right next to this rich organic material. And that allows us to measure 2 types of materials in very close proximity at our landing site. And from there, we can go further afield. The time when we get there being, in 2034, being a similar time of year as the Huygens probe descent in 2005, is southern summer, which means that the northern lakes and seas are in winter. And if they're not illuminated by the sun, if the sun's not up in the sky, neither is the Earth. And we're doing direct-to-Earth communication. So going to the North Pole isn't an option. However, the biggest questions that we have about the chemistry on Titan are the solid surface materials. That's what we don't know about. We don't know as much about. We have a better idea of the nature of the liquids in the lakes and seas. Now, that doesn't mean that one doesn't think that maybe in the long run, a potential extended mission would allow us to go further afield and dip the skids on the shore of a methane sea. But that's not the nominal mission plan. The water ice, the water ocean on Titan is quite deep. It's on the order of 100 kilometers deep. No, no. So there's a potential that there is water being erupted at a site of cryovolcanism or something like that, but we are not at this point looking into ways of getting down to the water ocean. And in terms of planetary protection, we also have, it's a much safer system to go to than a system with a thinner ice shell.
Not to be rude to the other questioners, but I'd really like to see the rest of the slides.
I'm almost at the end. In fact, I'm very close to the end. So this is a flight demo we did back in Maryland, back last May. This is about a half-scale model. It was a much windier day than we would see on Titan. If we had sound, you'd be able to hear the wind in the microphone. It was, in fact, the day before was too windy to fly. So it was much windier than we would encounter on Titan. It was great to see that even the half-scale model was nice and stable in the atmosphere, despite the Earth's dynamic atmosphere. Yep. Yeah, so what we do to fly on Titan, we use the MMRTG to charge a battery. And then we do all of the really high power intensity activities off of that battery. And then we have, so the Titan day is 16 days long. So no one has to live on Titan time, which is good. But it means we have a very long night to recharge the battery between activities. So we can do a lot of science activities, we can have a flight, we can communicate back and forth with Earth, and then overnight we would be able to make measurements, like we'd have the seismic monitoring would continue, the atmospheric monitoring would continue, but for the most part we would not necessarily do other scientific activities depending on the state of charge of the battery. But we could use that time to our advantage. There are a number of missions use nuclear power. Cassini, most of the missions in the outer solar system use the RTG type power source, simply because there's not a lot of sun. Juno at Jupiter is solar powered, and Europa Clipper will be solar powered, but those are some of the first to go that far and use solar power. So most of the distant missions do use these RTGs like we'd use on Dragonfly, but also some of the Mars missions. So MSL, the Mars Curiosity rover, is using a RTG, the same version of the RTG that we would fly. Yeah?
How many watts, how big a team do you need to monitor and plan once you land?
Right. So we have a big team already, actually. There are hundreds of people working on this mission concept on different aspects of it. The science team itself right now is 30-some people. But this is a long mission, and we would bring people in through participating scientist programs, through students and postdocs working with the team, because we'd absolutely, to do this kind of science in a New Frontiers program, you want to have robust community involvement. You also want to be able to bring new people in because of the lifetime of the mission. So we have a number of strategies for engaging the broader community so that we can, so we have a good scientific team and good community involvement. If we encounter an area where there might have been a cryovolcanic system, then yes, we would absolutely be able to look for the chemistry in that area where we know liquid water has been in contact with the organic material. I'm going to go over here for.
Just wondering, is the lack of oxygen in the atmosphere a problem? One, and what about the other moons?
The other moons are all fascinating in their own rights. Because we are a self-contained unit, we don't need an orbiter. The Dragonfly basically has an aeroshell. It's all buttoned up through cruise through the solar system. When it gets to Titan, we descend through the atmosphere. The back shell comes off. We drop the heat shield. The back shell comes off. We don't have an opportunity to look at other satellites in the Saturnian system. This is a Titan-focused mission.
Wait.
Yeah.
I was going to say, well, we have time for a couple
Yes, we
more
kind of
questions.
segued into the
We
questions.
sort of segued so quickly into the questions because it's such a fascinating talk. I just want to pause for one moment to thank Zibby for a terrific talk.
Thank you.